this last lecture is about how to screen from all these alternatives that we've talked about. So I'll give you some ideas on how you could pick an alternative. So we've talked about several management alternatives, and there's some others that we really didn't get into. But the bottom line is you don't have time or money to analyze all of these. And as you kind of gathered, we've sort of focused this workshop on you're in a planning stage of your study, not necessarily in like a design or implementation, but in a planning phase, which is where everything is since we're not really operating this way right now. So if you start out with this whole list and you just want to get down to a smaller array of things to look at, how can you screen? And here's just going to get right into it. So 2 big questions to start with. Is your sediment contaminated? If you don't know, then you have to go do some samples and find out if it's contaminated. If the answer is yes, it's a whole different set of considerations, a whole different set of options, and they're all going to be very expensive, okay? So you have to know that. If the answer is no, then you can continue on to the next set of questions. The next question is, can the downstream channel, with any level of reasonable constraints, accept sediment? Sometimes, and historically, there's been like a knee-jerk reaction to say, oh no, you can't put sediment in a river. And that's not true. We have put sediment in rivers all over the country. It's a permitted activity. It's not a forbidden activity. And there may need to be education of the stakeholders. You might need to do some research. There might be a process to get people to yes on this, but it may not be an actual physical, logical reason to say no, right? It might be fine as long as you can build enough consensus around it. So if it's truly a no, then you are left with dredging, with land placement, and hopefully attempts to reuse the sediment for something beneficial and trying to reduce the sediment coming in. But if it can be yes, even if there's constraints you can operate within that it can be yes, then continue on to the rest of these screening questions. I think I'm going to get this written out as kind of like a flow chart that someone could follow. All right, let's talk about drawdown flushing. How would you decide if drawdown flushing is a good idea or could be viable? One way to look at that is, well, where has it been done that it was successful? So this is a graph here with the x-axis is the reservoir capacity divided by the mean annual flow volume. So that's kind of like a residence time, because that will be years, will be the units there. And here we have residence capacity divided by the mean annual sedimentation volume. So that's kind of like, lifespan for the lake from a sediment perspective. And you'll notice that the lakes where this has been done and successfully done are all down in this corner of this graph. So smaller lakes hydrologically smaller lakes, relative to the amount of flow coming in is really where this is done. You see some lakes over here, and it says these were failures. So they did a flushing event, but they filled up again so quickly with sediment that it wasn't seen as worth it. And so they are, those lakes over there. So this was a plot by Sumi, who is in Japan and done a lot of work on reservoir sedimentation in Japan. Various other people have taken that same concept and plotted different lakes and tried to put on, well, what are the options that people are using, or what are the options that they might be using based on professional judgment of the person making the graph. So this plot was made by George Annandale, who has a lot of experience in multiple countries looking at reservoir sedimentation. And so what is plotted up here with all these little squares is storage operation, or in other words, we're just storing the sediment. We're not really managing it. All these little blue dots are check dams, which I interpret kind of as those dams that you had where they have check dams that then they have to clean out regularly. You had a different word for that.
Yeah, Italian call them sabo. Check dams, yeah.
Yeah, so sabo. So that's that kind of a thing. But then, similarly, as you get down into this range, you get into your flushing operations. So this graph can be helpful. You can plot where your lakes fall and see what George Annandale says are the likely options based on what has been done in other places. This graph, I believe, was made by Tim Randall, who's now retired, but from the Bureau of Reclamation. And it's just kind of simplifying, but it's based on the same data. And sluicing would be in this range. So that's that routing where you do, partial drawdown and try to pass the sediment through. flushing, down in this range. And the dots there are lakes from Kansas that Chris Ganau, who was of the water office at the time, plotted. So those are based on those fact sheets, so that the data is a few years old now. But several lakes in Kansas plot in that sluicing range, and then several lakes plot in that storage range, as to what people traditionally do. And Tuttle Creek Lake was sort of right on the border there of being in the viable, you could say, range for sluicing. Here is this plot again, but now we've got more recent data from the Kansas River Basin lakes. And so this has the various lakes, and there's multiple surveys for each lake. And so what you see is that over time, in general, lakes will move in this direction. So as they fill with sediment, the lakes get smaller, and in general then, even if a lake isn't really good for sluicing now, if you waited 30 years, it's now small enough, and the watershed size hasn't changed any, and it's still getting rain, and so then it might be viable in the future to use that method. This also has model results for future years on it. So we see Tuttle Creek Lake, getting out into the future when it's actually quite small. 100 years from now, it's practically Tuttle Creek Pond, and yeah, you could draw down flush it at that point. You wouldn't, there's not all that much volume left at that point. But thing just kind of shows the lake gets smaller, it kind of moves that direction. One issue I have with all these kinds of plots is they're often trying to say, what could you do to be 100% sustainable? And maybe that's very difficult to do with a large lake. You could do it, but maybe people aren't willing to spend the money that's required. But you could still prolong the life of your lake and make this descent into smallness take longer, just by implementing some of these things. So just because it doesn't show up in the right box doesn't mean you couldn't do it and it might not be beneficial. Okay. So for drawdown flushing, I would plot it. Where does it plot in this graph? And do that Atkinson analysis that Travis showed us. Very easy to do, right? That was pretty simple. And you can see how effective it is. Oh, first question before that, though, is do you have gates at or near the bottom of the lake? If you do, then you do these other things. If you don't, then you can move on. Sluicing. So with sluicing, you can see, again, where does it plot on this graph, as well as where does the trapping efficiency plot on your Bruin curve. If you're way up in this flat region, then you're going to have to draw down quite a bit to get hardly any benefit. If you're on the steep region, then drawing down a little bit might give you a big benefit. So that's kind of a screening tool. Hydrosuction. Do you have unused or rarely used conduits, water supply lines, or drawdown gates? So, and I've said this before, at some of our lakes, we have emergency drawdown gates. They're not service gates, but they're there just in case we need to drain the lake. Those could be repurposed for passing sediment. Other lakes have old water supply lines that were used at one point, but they're not being used now, et cetera. So, just how could water possibly get from one side of the dam to the other? Could any of those be retrofitted in order to pass sediment as well? And then, is the sediment of concern near the dam? Is it generally silts and clays? So if the answer is yes to both, hydrosuction is a strong candidate. Water injection dredging. Do you have discharge gates at or near the bottom of the lake? Is the sediment of interest near the dam and fine? Paul has left, so I don't remember what he said that limit on liquidity index was. 1.8. Okay, good. Everyone took good notes there. And then there's also the kind of a slope. Zach, do you remember what that is?
It's probably what we're going to find out too. But yeah, it maybe need to be a little steeper than that, but we think that 1,000 should be happy.
Okay. Which is pretty shallow, but anyway.
We're also creating saltfish.
You're also creating as you dredge, so we'll know more about this, you're right, as we do it. But okay. Dredging with downstream discharge. So anywhere that those first two big constraints are satisfied, is not contaminated, and the channel downstream can accept sediment, anywhere that is satisfied, you could do dredging and discharge the sediment downstream. There are some cases where it would strongly lead you to that direction, off the get-go, and that is if you have very stringent environmental sediment release constraints. So, for instance, I can envision places that the environmental community and the water treatment folks downstream could say, if you release during high flows, it's totally fine. You know, there's going to be high turbidity anyway, and it's going to be diluted by lots of water, and it'd be totally fine, but only during high flows. So you would need to get a lot of sediment out during high flows, and you'd have a hard time getting that much probably by these other methods. If you say, oh, you can release, but only the fines because we don't want anything to settle out. Or you can release, but only the sands and gravels because we consider that habitat and we consider the fines a pollutant. Or so there could be a lot of things where you could, with the control you can get from dredging, traditional dredging, that you could satisfy those. Okay. Or if the sediment you're trying to access is too far away to get it via hydrosuction, even though you've got some conduit you could pass it through, it's just too far away. Then you would want to do this. You could hook up your dredge pipe to that low-level conduit and still take advantage of the head, but you're just saying you have to add extra power to it in order to transport it that distance. Are the other options not available? Do you need to augment a less expensive option? So maybe you can get 10% of your sediment through something that's less expensive, but that's just not enough. So then you might also put a dredge on the lake and be doing things in combination. So if any of these things are yes, then this is a strong contender. And again, this was a lake, Millsite Lake in Utah, that was doing this.